All right, let's get started. So, yeah, how's everyone for the weekend? Good? Okay, let's see what we covered in our last lecture. So in the last lecture, we continued talking about conditional entropy. It should be conditional entropy. There's a typo. And also the chain rule of entropy, right? And then we introduced the concept of mutual information and the meaning of it. And then how can you remember the relationship between the mutual information, entropy, and joint entropy, and the conditional entropy, right? So, okay. All right, so yeah, for the chain rule, so we can write the joint entropy as this, okay? So basically, this is mainly from the Bayes rule, right? So if we consider it's a probability of y, then should we multiply the probability of x given y, right? Because entropy is taking the log out of the probability, then we have a plus sign here, right? So it should be relatively easy to remember it, right? And we could write entropy of y first, or we can write entropy of x first, right? They're the same. All right, and then we can generalize it to this form. Okay, so we're going to use this a lot in this class, right? The chain rule is very important. So today we're going to introduce you the chain rule of other quantities, right? So we're going to see a chain rule of, for example, mutual information, right? And we also have a chain rule for other things, right? Just to try to remember, okay? Yes, as we said before, right? So this is basically derived from this formula, right? So basically, this is by using the Bayes rule for like n times, right, to get this. All right, and then so we can consider the conditional entropy of this joint entropy, right? And then similarly, we can have our chain rule here, okay? And from now on, when we consider conditions, we need to be super careful, right? Because something can be counterintuitive, okay? Hopefully we're going to see some example today. If not, we're going to see that in the next class. Okay, and in general, so the entropy of y given x is not equal to entropy of x given y, right? So why is that? So because of this, right? So if normally we know this and that are equal, right? So why they are equal? Right? Anybody recall? So why this and that are equal? Or what is that? Hy minus hx given y. So what is that?
That's the mutual information.
Exactly, it's a mutual information, right? So on the left-hand side, so that's a mutual information between x and y. On the right-hand side is a mutual information between y and x. They're the same, right? That's why they're the same, okay? And since h of x and h of y are different in general, therefore, so this and that cannot be the same, right? So, okay, and the other thing is that entropy of x given x is 0. So the intuitive reason of that is, so if we know x, then obviously we don't have any uncertainty about x anymore, right? So there's no entropy. Okay, all right. So, okay, and then we introduce you the concept of mutual information. So this can be a bit tricky, right? Consider a particular outcome x, right? So the self-information of x is the uncertainty of x, right? And the conditional self-information x given y is the uncertainty of x if you know y, right? The difference of them represent the information or the uncertainty reduction, right? So basically it means that if you know y, then you can resolve this much of information, okay? And that is basically the concept of the self-mutual information, or the concept of mutual information in general, right? So the mutual information is nothing but the expectation of the self-mutual information, right? Remember that. So here, what we need to do is that the average is taking over all the joint probability distribution, okay, not the conditional distribution, okay? So you need to be super careful here, okay? And then we can see several properties of mutual information. So this is the definition of mutual information, right? And then, so we can write the mutual information as the entropy and the conditional entropy as a function of entropy and the conditional entropy. And then because we have a commutative property for self-mutual information, then we have commutative property for mutual information, right? So another way to prove the commutative property for mutual information is by using this guy, right, as we said, right? So this is the mutual information between x and y, and this is the mutual information between y and x, and they're the same, okay? Very good. And the other thing is that if they are independent, then the mutual information is 0, okay? But as we mentioned before, so probably we're going to see one example later in our class that, so if the mutual information is small, then we can now say that the dependence between x and y are weak. Okay. In other words, so if the mutual information, so I have a mutual information that's bigger than yours, I can now say that I'm more dependent than yours. Okay. So only when mutual information have a clear 0, then there's a clear meaning of the dependence of x and y. They're independent. Okay. Okay, and then the mutual information between x and we didn't mention that. The mutual information between x and x is basically entropy of x. Right? That makes sense? Right? Because if I observe x, then I know everything about x. Right? Then therefore I know the entire entropy. So that's a reduction of uncertainty. Okay? Very good. And so this is a diagram of kind of mutual information, right? This is an easy way to remember the relationship between mutual information and all kinds of entropy, right? So if let's say so the total area is joint entropy, right? And clearly the left-hand side is the entropy of x and right-hand side is entropy of y. Then h of x minus this h x given y would give you the mutual information, right? So you can use this figure to remember the relationships, right? Which is very convenient and handy. Okay, so all right, so now let's get started talking about today's content. Today is our lecture number 6, right? I probably will give you the first homework by the end of the week, right? But you are not going to be able to do all of them, okay? So just you should be able to do several of them, right? And as I said, right, as I'll give you a solution beforehand, and you can take a look. So all the homework problems are from our textbook, okay? All right, so today. First topic, so we're going to talk a little bit on the conditional mutual information. Then we're going to talk about the relative entropy. And then, so we're going to discuss, what we have learned so far. So we're going to talk more about chain rule, and we're going to see the chain rule of relative entropy and the chain rule of mutual information. Okay, and more mutual information. Okay, so that's the agenda for today. Let's see how far we can go. So conditional mutual information. Conditional mutual information. Okay, so now because our mutual information have 2 random variables, right? So now we're considering condition, right? Then at least we need 3 random variables. Okay, so we consider 3 random variables as follows. We have x and y and z. So the distribution of that is p, x, and y, and z. Okay, very good. Okay, so yeah, in order to define the conditional mutual information, so it's the same as before. So we're going to define the conditional self-mutual information, right? So basically, yeah, it's given by I of x, y, and given z. Okay, so yeah, based on the definition before, so that would be the difference between the conditional self entropy and self entropy and conditional self entropy, right? So now, because we have a condition on Z here, so the first term is a conditional self entropy, right? And then minus the conditional self entropy if I know both both Y and Z, right? Very similar to before, so that's the conditional self-information. Okay, so now given that, so this is defined on a particular X and Y and Z, right? And then we can take expectation on each of them, right? And then we're gonna have like 4 items, right? So yeah, let's see the first one. The first one is that how about we take an expectation over Y only, right? Then we're going to have the conditional mutual information written as follows. So for a particular X, and then we do an average over Y, and then maybe given a Z on a particular Z, right? So that's that's equals to the expectation. Okay, so here only on Y, right? Obviously, so I, X, Y, and Z, small z. Okay, right? And based on that, so we can take another expectation over X, and then we can have conditional mutual information between X and Y and a given Z. Given Z equals to small z, right? That's expectation over X and Y of I, X, Y given small z, right? So the next one, we can take the expectation over Z, right? So now we have the final form, so which is basically what we meant by conditional mutual information, right? So this is given by this, and now we take expectation on everything, so I don't need to be specify which random variable that we're going to take the expectation on, right? Then it is, right? So this is basically the definition of conditional mutual information, right? Okay, so here there is almost nothing new, right? Just very similar to what we covered before. Okay, so any questions? Okay, so maybe now you can think a little bit on, so what does this conditional mutual information mean, right? So given Z, and then we're gonna see how much information we can get, by observing also Y or X, okay? So think about that, right? So we're going to go back to this problem very soon. Actually, it's a very weird animal, right? And in information theory from now on, so you should be, every time when you see the conditional, mutual information or conditional entropy, conditional whatever, you need to be super careful, right? Things can go very counterintuitive, right? Okay, so next, let's talk about relative entropy. Right, relative entropy, I don't know, how much of you heard of this? Nobody? Yeah, somehow it's not a very famous name, right? But another name, you may heard of it, right? So it's also called callback Leibler divergence. Okay, or KL divergence. Okay, who heard of KL divergence? Yeah, that's much more famous, right? So, yeah, and also we're going to introduce you the concept of cross entropy. So that's probably a term that most of you heard of. Okay, so let's see why we have this, right? It's a very weird thing, right? Let's derive it from the beginning. So why we need relative entropy or KL divergence? Okay, so let's see motivations first. Okay, let's recall the meaning of self-information. Self-information I of X. So as we mentioned before, so this is amount of information needed to resolve the uncertainty of a outcome X, right? The amount of uncertainty of X. Okay, so let's write it down. So this is the amount of information or uncertainty needed to resolve the uncertainty of X. Okay, so what does that mean? Right, let's see this kind of example, right? So as we said, right, so mutual information tells you, non-mutual information, entropy sort of tells you the minimum amount of bits you need to represent one random variable. Right, let's see an example, see whether it makes sense or not. Right, so yeah, let's consider a probability distribution of X, right? Let's say the probability that X equals to, let's assume we have three values here. So X equals to 0 is half. The probability that X equals to 1 is 1 over 4. The probability that X equals to 2 is 1 over 4. Okay, so now we're going to use binary bits 0 and 1 to represent those random variables. Our goal is to minimize the average code length. Okay, for example, for the first one, you can use maybe like say 0, 1 to represent it. Second one, maybe 1, 1. The last one is 1, 0, for example. Does that work? It'll work, right? But is that optimal? Right, so now let's denote the expectation of the length of the, this is the length of the code. Right, then this equals to what? 2, right? Because everyone is 2, then it'll be 2 no matter what, right? 2 bits, right? So now let's compute the entropy, right? So the entropy equals to, with sum x over x, px log 1 over px, right? And in our case, hopefully still remember, so the first one is x equals to 0 is half log 1 over half plus 1 over 4. It's 1 over half, right? So it's not. Always do this. Yeah, I'll just write 2 here, okay? So 1 over half is 2, and then here is 4, and here is 4, right? So what does that equal to? Yeah, the first one is half, plus second one, 1 over 4 times 2, plus 1 over 4 times 2, right? So that equals to what? 3 over 2, right? Bit. Okay, I'm telling you that this is the best we can do. Okay, we're going to show you why, but not now. I just want to tell you this is the best I can do. Okay, okay. If you know this is the best you can do, then can you design the code? Right. So it's 3 over 2. What does that tell you? It's not an integer, right? So basically, it means that the length of the code cannot be the same. Otherwise, it will be the integer, right? Therefore, so do you have any idea how to design the code to represent each symbol? Yes?
Use like a 0 for the 1/2 probability, or just 1 bit.
Mm-hmm. And then?
Maybe like 1 for the other one, and then I guess you have to do 2 for the last one.
2 for the last one, like how?
I'm not sure.
Yeah, if you compute it.
I don't know how can you tell if it's like one of those and one of
Exactly.
those? Yeah.
Exactly. Yeah. Yeah, I will just comment what he said, right? Did everyone get, what's your name?
Carell.
Carrel.
Carrel.
Carrel. Okay. Did everybody get what Carrel said? For example, if you say here's 1, 1, is there a problem? It is, right? Because if we receive a 1, 1, we don't know whether it's two 1s or 1, 2, right? So it means that this guy is a prefix of this guy, which is not good, right? When you design a code, avoid this kind of situation. Okay, it's called prefix code. Okay. If you compute, the average length of it, you'll see that it's even less than 3/2.
Okay, maybe
right.
for the middle one, use like 1, 0.
Exactly.
So anytime, yeah.
Okay. How about the last one? 1, 1 work?
I think 1, 1 should work.
Yes.
Yeah.
Right. So now, if you can just count, right? So if you receive a 0, then you know it's the first one, right? If you receive 1, 0, right? It's a second one because this is a 0 has to be like single, right? You need to count this, Therefore, you can double check. This should work. Okay. So now. So what's the idea of it, right? It's like if a symbol happens with a higher probability, then we need a smaller code length, right? A lesser probability, then you need a longer code, right? So that's basically the key idea, right? Okay, and if you look at it very carefully, right? So basically, from this formula, actually it can tell you something, right? So for example, for the first one, for this guy, so that's 1, right? That's for the first symbol. And for this guy, it's 2, right? That's for the second symbol, right? And then now this is also 2. So this is the length for the third symbol, right? So basically, roughly it tells you that, okay, now the code length for x should roughly equals to log 1/px, which is the self-information of x. Does that make sense intuitively, right? It's not accurate, rigorous now. So the reason I'm saying that, is approximately equal is because of the number here, right? If the number, log this, it's not an integer, then we cannot do that exactly, right? Roughly speaking, that's the case. Okay. So yeah, but that's not the topic, where I want to focus now. I just want to give you, an intuitive example showing you that actually, this could be the code length, right? Actually, one physical meaning of self-information is how many number of bits you need to encode each symbol. Okay, so now, let's go back here. So basically, now let's consider the PMF of x, right? So based on what we said, okay? So we know that the code length is a self-information, right? That's equal to log 1/px bits. Okay, so this is basically, if we know px, right, and then we're going to use this number of bits to encode each symbol, and then we're done, right? And that's optimal. Okay. But in practice, normally, do we know px? No, right? So we're going to estimate px. Okay, so now I'm going to write another symbol, another PMF. It's called qx, right? So qx is nothing but the estimate of px. Okay, estimate of px. Okay, so now because you don't know px, but you have an estimate of px, then you're going to use qx to do the encoding, right? Because you don't know px. Okay, so now the code length. Again, so this is the code length equals to log 1/qx for each small x, right? Does that make sense? Right? We don't know px, we'll have a qx, which is the estimate of px, and then this is the best we can do. Okay? And now let's compute the average code length. Okay? So the average code length is an expectation of Lx here, right? So that equals to what? So the expectation would be over what? Over P, right? Because P is a real distribution, right? Although you don't know that, but it is a rule, okay? And then, so we're going to do inside is log to 1 over qx. Okay, and if we write it out, it'll become a summation of this px log to 1 over qx. Okay, so did that ring any bell? So did you see that before? So we'll give a notation here. We call that h pq. So this h, we use h, right? It does, it should be related to sort of entropy, right? Yeah, for this formula, did anybody see this formula before? What's that? Yeah, so who learned machine learning before? Yeah, I know some of you, right? Don't be afraid, right? Who learned machine learning? Did you recognize this? Really? Nobody? Interesting. So how about if I put this 1 over to a negative sign in front?
Like the distance of the estimate the distance of the estimation to the real distribution.
Yeah, that's the meaning of it, right? But actually, yeah, I don't like the word of distance, but I see what you mean there. So this cross entropy. Oh. So this is called cross entropy. Okay, so that is the objective function or the loss function for large language models and many other applications, right? So now let's see whether it makes sense or not, right? So we're going to come back to this later, but one thing we can immediately see is that, so if let's say, so we want to minimize that, right? So it's a loss function, right? In practice, we want to minimize that. So what does that mean? I mean, there's several meaning of it, right? So one easy way to see is that, so this is basically this function, right? P is something that we cannot control, right? So normally in practice, how we compute that, we just compute a average of it, right? We do lots of sampling and then we add them together, right? That's the approximation of the expectation, right? And then we minimize it, which is equivalent to maximize Q, right? What is Q? Q, so in large language model, Q is nothing but a conditional probability, right? Given all the input, given all the previous text, what is the probability of the next text, next word, next letter, right? That's, this is what large language model do, right? So it doesn't really have a, objective. It just want to estimate, the next word, next sentence, next letter, right? So in practice, it just maximizes conditional probability, which makes sense, right? So if we have some estimation, so which is to maximize some probability, conditional probability, what is that estimation called? Want to maximize Px given y. What is this estimator? Right? By observing y, then want to maximize, find the x to maximize Px given y. What is that called? Nobody remembered? Yeah, I'm pretty sure that many of you learned that before. Say it. Exactly. Yeah, it's a maximum likelihood, right? So what large language model does is nothing but a maximum likelihood estimation. That's it. That makes sense? Okay, yes?
So for the Qx is for the estimation of the Px, but is that based on the Px is unknown? For example, like you have some unknown thing, how do you get?
Yeah, Px is always unknown, right? There's no, you can only estimate it. Right? So in real world, there's nothing is known, right? We always estimate something.
So would Px just be like the distribution of like the training data?
Yeah. Well, yeah, you can think in that way. Yeah, but we're gonna go to, not exactly, but we're going to come back to this later. So, yeah, but more or less, yeah, it should be in that. Okay, yeah. So this is some understanding of the cross entropy, why it can work so well, right? Because it's nothing, but we are doing ML estimation. And the other thing, that is kind of intuitive, not, it's hard to explain, is that, from Shannon and from also some other famous researchers, and people believe that you can, if you use shorter bits to represent the information, then the better, right? So if you look at this, as we said, right? So if the estimate of px is qx, right? And by using qx, actually, if you want to encode this information, so this is the smallest length you can get, right? Therefore, it basically means that that's the shortest number of bits to represent the information. Okay, which is beautiful, right? So now we have two reasons to use cross entropy as the loss function. Okay, there's another reason actually. Okay, so in order to understand the other reason, then we need to understand what is relative entropy, right? So we have not introduced that yet. Okay, so let's summarize it. So let's write it down. So the meaning of this, the average code length, is that we need this number of bits HPQ. Yeah, this order is important, right? P means the real distribution, Q means the estimate of the real distribution. Okay, we use this number of bits to code. Okay, by using code QX as an estimate of PX. Okay, so this idea is very important. Okay, great. So now let's continue here. So let's recall that entropy of X looks very similar to this, right? So entropy of X is nothing but we do an expectation over P, obviously, but the difference here is that we do know Px, right? So this is the entropy of X. Okay, so now how about we want to see what is the relationship between this guy and this guy. Okay, so this, is the kind of entropy, but we use Qx. So this is a true entropy, right? First of all, so which one you think is larger? Bigger? Yes.
H of PQ.
Exactly. Why?
Because it's more uncertain. We're doing an estimate instead of having the actual data.
Yes. Yeah, because as we said, right, this is the smallest number possible, right? And anything else other than that would be bigger, right? Yeah, in this case, what you said, right? So in this case, we use a Q as, which is not a true estimation, right? Definitely we're going to have a bigger number here, right? So then how about we compute the difference between these two? Right, the meaning of that is, so it's a degradation caused by using Qx instead of Px to code. Right? Or in other words, so this is how many more bits you need compared to the optimal or the smallest number of bits. Right? That makes sense? Okay, so now let's try to compute it, right? So we know this guy equals to Px, Qx, sorry. Px log 1 over Qx minus Px log 1 over px. Okay, very good. Right, and then we can combine the px part, right? And then compute the difference between this guy and this guy, right? If we do a minus here, then the p will be upstairs, right? So now we have a log px over qx. Okay, and then we're done. Okay, so this is called relative entropy. Or KL divergence. Okay, very good. And we denote that as d p q. Okay, so this is a notation. Therefore, we can write HPQ as Hx plus the relative entropy. Okay? Okay, great. All right, so, okay. So this is relative entropy. Oh, by the way, so I think, for the traditional information theory people, so they call this relative entropy instead of KL divergence. Okay, so the reason is that, so divergence, it makes people feel something related to distance. Okay, so we're going to see that in a minute that the KL divergence or relative entropy is not a metric of distance. Okay, we're going to see why. All right, so yeah, let's give the formal definition of the relative entropy. The relative entropy between two PMFs, Px and the Qx is defined as, so I think in the book it just used P and Q here, but normally, yeah, we write in this way. Okay, we're going to see why, right? Again, so that equals to this formula, right? And then we can also understand this as an expectation of P, right? Because we have a Px here, right? Expectation over P, and then what is inside is Px over Qx. Okay, so that's an expectation of this quantity. So that's the relative entropy. Okay, and now let's see an example of relative entropy, right? Actually, we have seen a special case of relative entropy before. Okay. Yeah, that's a sound of, it's find me, right? Okay, so let's compute the relative entropy between Px and y, so the joint distribution, and also Px times Py. Right, let's see what does that equal to. Okay, so by definition, so this equals to, we have x and y in x, let's write in this way, right, x and y. And then we'll have Pxy log Pxy divided by Pxpy. Right? So what is that? So did that look familiar? What's that? Mutual information. Right? So that's equals to mutual information, x and y. Okay? Therefore, the mutual information is nothing but relative entropy between Px and y, and the product of the marginal distributions. Okay, so mutual information is a special case of relative entropy. Okay, very good. So now let's see the properties of relative entropy. Okay, so the first important property is this: d p q and the d q p are they equal? Yeah, if you write down the formula, right, they're totally different, right? Because the formula is not symmetric between P and Q, right? P here, Q only downstairs, right? If we flip them, of course, in general, they're not equal, right? They're not equal, right? So therefore, this is not a distance metric, right? If a distance, the distance between x and y, the distance between y and x, they're the same, right? So in practice, many people use relative entropy as a metric like distance, right? So people say, okay, yeah, I'm going to say that later probably. And the second one is also related to this, right? Another reason it is not a distance is that it does not satisfy the triangle inequality, right? What is triangle inequality? So for example, let's say if I have 3 points here, right? So we know this is a distance, right? This is a distance, this is a distance. Okay, let's say you have A and B and C here, and let's say this distance is R1, this distance is R2, and this is R3, right? And obviously we know that R2 plus R3 should be bigger than R1, right? If it's distance, it doesn't satisfy this condition, right? It's called triangle inequality. Okay, but relative entropy does not satisfy that. Okay, it's very important. So normally people think relative entropy, it is sort of distance, right? Because people think in that way and use it in that way, and it works, okay? But it's not a distance, okay? Sort of distance between two distributions. Okay, but not exactly, because D, P, Q, so it does not satisfy that, right? So less than D, P, R plus D, R, P, right? So this not true. Okay, it does not satisfy the triangle inequality. So it's definitely not a distance. Okay, and the third property is that, so if for some x, okay, and qx equal to 0, okay, meaning what is downstairs is 0, right, and also px is not 0, obviously, okay, then the KL divergence is infinity, right? So this can be arbitrarily large. Okay, and lastly, so yeah, because of our idea, right? Our idea of KL divergence, so it's the actual number of bits we need, to do the encoding if we use Q, right? Therefore, it has to be bigger than or equal to 0. Okay, so that's intuitive, right? But we can also prove that, why it is bigger than or equal to 0. Okay? Yeah, let's show that. Yeah, let's do that in the next page. Proof. Okay, yeah, prove the last one, right? Why this is bigger than or equal to 0. Okay, so let's see how we can prove it. So yeah, let's write down the definition first. So what we're going to do is that, so it only makes sense when P is bigger than 0, right? If P is 0, then the corresponding term will be give you 0, right? So just consider, a set A here, where A corresponding to all the x that Px is bigger than 0. Okay. Yeah, we use a ln here instead of a log base 2 for simplicity. Okay. This ln basically based on E, right? Based on it's a natural log. Okay, and here the set A is nothing but for all x such that Px is bigger than 0. Okay, or this is the support set of x, okay, random variable x, okay? And then, so what we can do is that we can take a minus sign in front and take Q upstairs, Okay, the next is very important. So basically now we're going to use the important property of a log function, okay? So if we draw this natural log, you're going to see that. If it's not the natural log, maybe it's not like that. But if it's natural log, so this is ln x, right? And then if we draw another line here, so you're going to see that, right? So this line is 1 minus x. Sorry, x minus 1. Okay, so what you can say here, the intersection point here is basically 1. Right? What you can tell here is that x minus 1 is bigger than ln x. Right? So basically, we're going to use this inequality here, right? Here we have a minus log, right? So the minus log here would be what? Bigger than, I mean, there's an equal sign, bigger than or equal to 1 minus x. Right? So we're going to use that here, right? We have a minus ln here, right? So that's equal to basically, or should be bigger than or equal to x in A. And then we're going to replace it by 1 minus x, which is 1 q over px. Right? So this step, we just use this inequality here. Okay? And then it should be easy. So the first term is 1, right? So we're going to sum over this guy, and then we minus px multiply qx px. Okay, and so we know that this guy should be equals to 1 because the excluded term are all p equal to 0. Okay, and how about this term? So here we can see that the px canceled is sum over qx, right? But since A is not the entire set, so this guy is less than or equal to 1. Right? Therefore, together, this should be bigger than or equal to 0. Right? Okay, and another important point is the equal point here, right? So here, we can see that, so this equality holds only, let's say, if and only if, so the double direction, if and only if x equals to 1. Right? So in other words, so basically, it means that, so let me use, now the equality holds if and only if px over qx, or qx over px, right, equals to 1. Right? This means that px and the qx are the same. Right? Which kind of makes sense, right? Because when they are the same, then we do not need any extra bit to encode, right? Therefore, this difference should be 0. Okay? And then we're done with the proof. Okay, so let's finish today. So we're going to continue talking about that in the next lecture. Okay?